Hey YouTube, and happy Wednesday. It is a Wednesday. It's getting close to 11:30 p.m. Eastern Standard Time, which means it's time to record another video for the channel on this fine, rainy, windy, cold Wednesday evening. Tonight's video will be about another minimalist computer that I will be replicating and talking about extensively in coming weeks. This computer or computer teaching aid, this mechanical computing teaching tool, is called the Cardiac computer. I just want to go through a few web pages about this and give some background as I did for the Kenback before I attempt to build one. It's called a cardiac computer because cardiac is an acronym. It's an acronym for Cardboard Illustrative Aid to Computation. It is a computer in some sense. It's a piece of paper, a couple pieces of paper with moving sliders that replicates the core of a processing unit or a core of a computer along with some memory that's not shown here. But it's really intended as a learning aid for understanding how computers work. As it says here in the Wikipedia page, it was developed at Bell Labs, a very famous institution, in 1968 by David Hagelbarger and Saul Fingerman to teach high school students how computers work. The kit includes both an instruction manual and a die-cut cardboard computer. In my future videos, I'm planning to print this out on thick printer paper and to laminate it and cut it with a Silhouette Cameo. And I'll show in a few more minutes some web pages with descriptions about how to do that. Like I said, it is sort of a mechanical computer, but not like, say, a Curta calculator or Babbage's Bones or even that music box I showed you. The computer works by sliding cards and entering in instructions, memory, and results in the accumulator by pencil. I'm planning to make a laminated version, so when I do the demo, I'm planning to use a wet erase marker most likely, so I can easily write lots of instructions and clean it up fairly well. I'll have to see how feasible that is. The arithmetic is done in the head, a very powerful low wattage computer of the person who is operating the illustrative aid to computation. It operates in base 10, so that's nice and easy to manipulate for us humanoids. And it has 100 memory cells which can hold signed numbers from 0 to negative 199 or negative 999 to 0, and then 0 to 999. The instruction set is just 10 instructions, which include addition, subtraction, tests, shifts, input, output, and jumps. The CPU of the computer includes 4 different slides that move various numbers and arrows to have the flow of the real CPU, which is the user's brain, move the right way. So those slides really are a guide for you doing the computation from step to step. What's not pictured here is the other half of the cardboard cutout, which has 100 different memory cells. Cell 0 is a ROM, always containing numeric 1. Cells 1 through 98 are RAM, available for instructions and data, and I'll have to get into this further, but cell 99 is described as EEPROM. I just talked about what memory cells can hold. They're running with a pencil. There's something kind of cute. There are little bugs that you move from memory that I'll show you in a bit that act as a program counter and placed in a hole besides the current memory cell. Before I go further, I just want to show that there's a cardiac emulator here that is showing a power of 2 program that's supposed to output different powers of 2. 1, 2, 4, 8, 16, 32, and so on up through 512. That goes through 277 steps. In future videos, I also plan to show implementation of a cardiac emulator, most likely for Palm OS, just to tie together a few different themes on my channel. I mean, maybe I'll eventually have a YouTube video where I take my bike somewhere and have a real cardiac computer replica and a pannier and a Palm OS computer with a cardiac emulator on it, and I can show you cardiac computing on the go. Another really exciting video I'm planning once I build this is to do cardiac cloud computing with a friend of mine, Scott Haley. I'm planning to build, once I have the cardiac computer built, have Scott create a countdown program in cardiac machine code, and then over a Zoom call, he can send me the instructions and I can execute them on the cardiac. Therefore, we have cardiac cloud computing, paper computation over the cloud, which is both humorous, entertaining, and I think also will be really thought-provoking. Okay, so with that digression, I'll get back into the description here. The cardiac programming language is a machine language with 10 different instructions. Instructions are 3 digits. Zeros is the opcode, or sorry, the first digit's the opcode, and then the second 2 digits are the address acted upon. Addressing is one of accumulator to memory, absolute memory to accumulator, input to absolute memory, and absolute memory to output, which means I guess there isn't indirect addressing in this language. High-level language has never been developed for cardiac, not surprising. Now let's just go through the instruction set before I go through a couple more pages on the cardiac computer. 0 is input, that takes a number from the input card and puts in a particular memory cell. 1 is clear and add, which empties the accumulator and adds the contents of a memory cell that's specified in those second 2 digits. That's kind of cute that, you know, there's 3-digit instructions there with the opcode and operands, and adds the contents of that specified memory cell to the accumulator. 2 is add. What is add? Adding is adding. That instruction adds the contents of a memory cell to what's already in the accumulator. It does not clear beforehand like CLA does. TAC, or opcode 3, tests accumulator contents. It performs a sign test on the contents of the accumulator. If minus, you jump to a specified memory cell. 4 shifts the accumulator X places left and then Y places right, where X is the upper address digit and Y is the lower one. That's kind of interesting. I'll have to think about the different consequences of that. 5, or output, takes a number from the specified memory cell and writes it on the output card. All this seems to be sort of reminiscent of a machine that uses punch cards or you know, some kind of input and output like that. I mean, it's obviously a paper computer, so it makes sense. 6 is store, that copies the contents of the accumulator into a specified memory cell. That's interesting. I mean, a lot of these almost make me think of like different move instructions that are, you know, specified as distinct instructions just based on what the input and output are. Okay, so 7 is subtract, subtracts the contents of a specified memory cell from the accumulator. Jump, jumps to a specified memory cell. The current cell number is written in cell 99. This allows for one level of subroutines by having the return be the instruction at cell 99, which had 8 coded as the first digit. That is really interesting. Oh, and this is the EEPROM idea there. So that's how it's like electronically programmable ROM. You got a single cell for that, so enjoy it. Enjoy those 3 digits there. And finally, 9 is halt and reset. Move the bug to the specified cell and then stop program execution. Programs are run by first sliding 3 slides to the number in the instruction register matches what's in the memory cell. After that's done, the bugs move to the next memory cell and the user follows an arrow which tells them what to do next. I think there was, you know, one other card. So there's, you know, input, and then something I talked about a second ago here. Oh wow, cells are erased with an eraser. Bug acts as the program counter. 4 sliders that, yes, so 4 sliders to move various numbers and arrows to have the flow of the real CPU move the right way. Okay, so let's go through some other pages here. There's a much nicer overview, and by nicer I mean a lot more thorough and a lot more organic on Drexel's CS page. I'll copy all these links into the description like I did for the Kenback. This just gives some background about the cardiac. In July 1969, Bell Labs record contained an article describing the system and materials being made available to teachers for working with it. I heard a very funny joke about the cardiac. I have several, I'll mention here just to keep you all interested 10 minutes in. A funny joke that I thought my computer instructional tools in high school were bad, and I didn't realize some people had to use cardboard ones that could get destroyed in the rain. I can follow up on that joke by saying the ones I make will be laminated, so you can't say that the rain ate your homework. Another joke about cardiacs is if you come across an error, they go into cardiac arrest. Another one, and I love accounting. I don't mean this as shade. When I prepare one of these, I can think of it as creating an accounting degree. Just kidding. I also had joked with people at work that if we had a building full of these, we would be the world's largest Y1K, 2K, and 3K compliant accounting firm. But anyway, tasteless jokes aside, the cardiac computer consists of a left-hand CPU section and a right-hand memory section. There are 5 sliders on the CPU. This is helpful since I didn't really go through this well in the previous article. There's one slider of input cards, one slider for the accumulator sign, and then 3 sliders for the digits of a particular instruction. The memory side has a single slider of output cards. The portions of sliders show through cutouts in the card frame. Cutouts for input and output sliders show the current card to be read or current card to be read or written. Accumulator sign and 3 instruction sliders show steps through cutouts that describe operation of the selected instruction. So that's great. The sliders and cutouts are the instruction decoder of the CPU. Each memory location has a hole in it, and there's a cardboard ladybug. In my case, it'll be a laminate paper ladybug that serves as the program counter. 50-page manual. I know, I think it's Tom Higgins has some videos on YouTube showing that. I'll, as I mentioned, do another set once I have this printed out. I saw a couple different versions. One, the original here has different shades of green. Another more modernized one that's black and white. Some sections on bootstrapping and subroutines. That's kind of cool. Flow charts, definitely. There's a lot that could be done with this. There you open the cardiac. See if I can get a better picture there, a bigger picture there. Yes, so there's the instruction decoder here, and it tells you, to copy the input card into, a particular cell. So, oh, that's interesting. So what's happening is you have 2 sliders here that change the operand, or usually the address, and then this third card is telling you what the instruction is. So that's great. You don't have to remember that off the top of your head, which is sort of obvious. Advanced card, let's see, accumulator test is card blank, advanced card bug to cell 00, and halt, move bug ahead 1 cell. You can enter things in the accumulator. Yeah, it's unfortunate there's some glare there, but I guess that's to be expected. So you have address 1, address 2, opcode here, and all this extra information. These other sliders, accumulator test, positive or negative, input and output. And there's your cute little ladybug there. Oh, and the bell logo on the left. Okay, so a little bit about the CPU architecture, memory addresses. Oh wow, data into the ALU, and then into the accumulator. Yeah, I'm not doing a very good job there. Data for the instruction register and decoder and arithmetic logic unit is decoding the instructions and taking data and acting on it through the accumulator, and advancing the program counter through memory addresses. Although the cardiac's memory can only store 3-digit numbers, you may be puzzled by the inclusion of an extra square in the accumulator. It's there to handle overflow. Yes, you'd expect overflow when you add 2 3-digit numbers, and it just happens, those add up to more than 999, 500 and 500. There you go. Input and output device. These are a card reader and card punch. Those would have been very relevant at the time. Some nicer description of the encoding, the opcode and addresses, or oh well, that's the shift accumulator, left and right. The left shift count is given by floor of A over 10 and right by, oh well, A modulus 10. Lower doesn't treat the lower digits as an address. Okay, sure. So we had talked about that. Instruction execution, some more symbolic notation here. Accumulator contents, program counter, operand address, contents of memory location X, input and output, no indirect addressing in this CPU, and just some nicer symbolic notation of what these instructions do. Assembly language format organized in these 6 columns. That is really cool. Oh, wait. I noticed that the only way of specifying the address of a memory location we want to use is in the instruction itself. Most computer architectures, like I talked about, have indirect addressing, where the address we want to use can be stored in a register or another memory location. Variables which contain memory addresses are usually referred to as pointers. This is really cool. Even though I'm just reading off the page, but this is so exciting. Pay close attention here. Although the Cardiac doesn't have hardware support for using pointers directly, we can do simple indirect addressing. Suppose we have a variable stored in a memory location called pointer and it has the value 42 in it. Now if we want to load the accumulator with the context of memory location 42, we can do something like clear the accumulator, add to the accumulator the data stored in pointer, and then I guess store that in the indirect load location. If I'm following that right, which would be 23. Notice that even though we've specified that we'll load from location 00 in the instruction at location 23, we have changed it to load from location 42 by the time we execute that instruction. Okay, gotcha. Yeah, I'll have to look at this a few more times. Yeah, clear the accumulator and load what's in 00. By the time for that matter, it doesn't matter if we load anything into location 23 before starting the sequence. It'll get set before we use it. Oh, I see. Because store indirect load is storing in location 23. Interesting. Okay, yeah, I'll have to wrap my mind around that. Arrayed indexing stacks. This is really cool. I'll have to go into a lot further depth in future videos. Recursion. Look how complicated you can get with this. There's a cardiac simulator they have on this page. This is really cool. Some examples. Counting example, list reversal. Powers of 2 that I talked about, towers of Hanoi. There's a lot more stuff here that we could go through. Pythagorean triples. Look at all these problems you can solve just with a paper computer within 100 instructions. Very cool. Okay, so I'll go to a couple more pages here. Michael Gardy, who has a great YouTube channel, has a description of how to make a cardiac computer using laser cutting. Yeah, just more background about the cardiac. And let's see. Yeah, 110-pound cardstock. You can laminate it. I'll see if I can get away with thinner paper, but I think my laser printer can handle 70-pound paper maximum. So I might try lighter and heavier paper, just experiment with it a bit. Color, used a color printer as makerspace. Yeah, you could. I want to print it off in 20-pound paper and just show you the different sliders in like a prototype video before I make the full thing. There's the SVG pages. You can see how you get this all cut out. That's really cool here with the instructions. Place a magnetic sheet behind the memory panel and install small magnets to the tip of the ladybugs. That is really cool. This will prevent an errant sneeze from causing you to lose your place while executing the program. I hate it, when I sneeze and I crash my computer. Okay, there's the assembly directions. That is so cool. I can't wait to do this. I think he had something up here about laser cutting. Yes, here we go. If you're fortunate enough to have access to a laser cutter, I'm going to use a traditionally used for vinyl die cutter, a Silhouette Cameo. I'm also going to do a demo of how you can interface that with Linux. I know there's Inkscape, Silhouette Cameo, interface mechanism that's already been set up, so I'll definitely do another video on that. Okay, and there's your assembly process, and you see it's actually quite complicated behind the scenes there. Final thoughts, that's it. You have a fully functional computer simulator. My small high school in Northern Ontario got enough of them for a whole class, so it must have been a lot. Despite that, cardiacs are impossible to find today. Nothing like a real device. Okay, so that's great there. There's a little bit here on perma computing about the instruction set and so on. Again, I need to go back to that indirect addressing. That was really cool that you, even in a system that doesn't explicitly have indirect addressing, you can create a mechanism of indirect addressing. And then Johann von Kano has a great page about how you can get this get this printed and cut with a CNC knife, or in my case, a die cutter. Artwork with manual lines for manual cutting and one without lines for CNC cutting. The CNC version has pass marks to auto-align the printed graphics with the cutting path. That's awesome. Testing on a Silhouette Cameo, that's what I've done. So I'll definitely use this version. I'm going to print out this version and another more modern one that's sort of a simulation of the simulation that's all black and white graphics. Programming the cardiac, it's easy to build. Just print, cut, and put the slides together. I added numbers to avoid placing them in the wrong order. Oh, that's kind of cool. Skip cutting the round holes for the program. It's tedious. Yeah, that's a pain. Small stone, like Michael mentioned, and I might try that. Putting a little magnet on the ladybug. That is so cool. You can do your computation in your head with the aid of this computer. Someone mentions, John Kirwan mentions that he had a lot of tiny holes cut with an X-Acto knife. There's some details in doing this manually. That's truly wonderful. That is great. Well, I have a lot in store. A lot in store for the future. A lot of work to be done in the future here with the cardiac computer. And with that, I conclude the video. I hope that was helpful, interesting, and maybe entertaining to you. I look forward to putting together the cardiac computer and testing it. I think, for my next video about this, I'll just print out these different components on regular printer paper and see how that looks. Also, laminate, we'll try laminating and cutting just regular printer paper, maybe some heavier printer paper. And I'll have videos about how to use this laminator that I got, a real simple Scotch laminator. I mean, that's pretty simple, but I thought I might as well have a tutorial. And another one about how to use a Silhouette Cameo die cutter with Linux, with that interface to Inkscape from what I read, but I'll get more details ahead of time. And with that, thanks so much for watching. I hope you have a great rest of your week, and please like and subscribe as always if you enjoyed this video and you'd like to see more similar videos in the future. Have a great one.